going to talk about solutions now. Yeah? But before we talk about solutions, I would just like to talk a little bit about what I think are false solutions. Yeah? So, I have a question for you. If you were told that there are 423 architecture colleges in India and only 1/4 of them have even one course about the environment, but the word environment, climate change is mentioned in only 100 out of the 423 architecture colleges of India. And from that, from those 100 colleges, only 5% of the content has to do with the environment. What would you say about that education? Is it fit for its purpose? No, right? We can't have a situation where the education of architecture primarily, I focus much more on that, so sorry if I don't represent too much about the civil engineering curriculum right now, but we've examined the curriculum of a lot of architecture universities in India, and we found that there is underrepresentation, gross underrepresentation of environmental and climate related knowledge in our curriculum. It need not be everything, for sure. You do need to learn lots more things, structures and theory, and how space and aesthetics and everything, absolutely. But I'm sure you agree that 5% of your entire curriculum being about the environment is not proportionate to the scale of the problem. Okay. How many of you believe that if everybody became green certified architects with a LEED AP or a GRIHA certification or GRIHA certified professional, that this would be enough? That all we need to do is just go and do all these certification courses. Any of you sincerely believes this? Okay. Even if it were true, let's look at how we are performing. So the green building movement in India started around 2000. Yeah? Around 2001, I believe. It's been what, 20 years? In 20 years, out of the 61,000 registered architects in India, 62,000 registered architects approximately, it must have increased by only 2,915, which is 5% of architects have been to a green certification program. Yeah? And has anybody here participated? Is anybody here a IGBC accredited professor? You are? Anybody else? Okay. Here in this room we have one person, right? I'm sure that it still doesn't equip you with sustainable design knowledge, right? It gives you a way to do the certification process and some knowledge, but it's relatively at the surface. Yeah? So green rating is not going to do it. What? Only brilliant. Yes, it's only the what and not how. Another thing we all talk about, okay, green buildings, we need to make all buildings in India green. 22 years since the movement started, out of the 44 billion square feet that India has, only 1.8 billion is certified green built space in India. So, of course, it's a part of the solution, but it's moving too slow. Which is why we cannot rely upon the end of the pipe of the problem. End of the pipe means you've already put the pollution into the pipe, now you're going to be putting some treatment system at the end of the pipe. We need to go to the beginning of the pipe, where these ideas, where the how is sort of being constructed, where that discourse is happening, which is here. Here and in the professional practices, we need to work there. And that's why, frankly, I'm here, actually. Because our understanding is that working at the green building end, working at the technology end is all good, but it's too little too late for a situation where we have about 8 to 10 years to turn things around. Okay, so these are some facts that I already told you. Now, contrary to what most people believe, India actually has very clear and stringent targets that it has made commitments to. Okay? So, basically, here are the commitments that India has to the world. So, the world's goal, by the way, is by 2050, we must reduce our footprint across the world by 50% compared to pre-industrial levels. Okay? We need to cut down our footprint by 50%. That's the world's goal, which means it needs to cut down 15 billion tons of carbon dioxide a year. Now, we're really going to get into actual calculations in a bit. What is this ton of carbon dioxide, and how do I get to know what the footprint of my building or of your own life is? Okay, very quickly we'll do that. But the targets for India are this. India has said that we will reduce what's called the greenhouse gas intensity of our GDP, which means we are going to grow, but per rupee of growth, I will emit 33% less pollution. So this is the deal we have struck, saying that you cannot question our growth, but our growth will be cleaner from here on. Okay, that's fine. So one good target to have for your projects is we don't have to go for net zero energy building always. How many times are you going to get a client that gives you net zero energy building? Very rare, right? It's going to be a theoretical NASA project and those kinds of things. So what we're looking for is not event architecture that is green. You know what event architecture is, right? Every architecture firm will have this one flagship project that it will keep showing everybody. This is what we did, but the rest of the stuff is all trash. What we are talking about is all projects should be about 33 to 35% cleaner from now on. Set that target for yourself. Can I make a building that has 33% less impact than business as usual? That's our commitment to the world. Okay. In terms of reducing refrigerants, also India has a consumption as a target. By 2028, 6 years from now on, we cannot be buying or selling any more what are called conventional refrigerants. In 6 years, we have to get rid of them. And then we have to start cutting down whatever air conditioning refrigerants are already there. This is a commitment we have made. 6 years, do you feel prepared? In 6 years to design a building that doesn't use refrigerants. It's going to come hard if we don't prepare now. And then you know what will happen? A bunch of consultants like me will be around and be like a pack of wolves because you would not have the knowledge, and then will become architects again, having to hire expensive consultants, which would be a real travesty. Instead, we could just learn how to do it now, ourselves, without relying on consultants. Okay, India has a lot of reasons to be hopeful. See, we only have 74 million ACs, right? Other countries, for example, we all love to compare ourselves with China. Do you know how many ACs China has installed in its entire country? 1 billion. 1,000 million have already been installed. So they are in a way screwed. Because they've already installed all this higher energy consuming, high global warming refrigerant based air conditioning, and now they have to retrofit and they have to undo. They have to go in reverse direction now. We are not so saturated yet. Our story has not been written yet. So this is a great place for us to start. We can avoid what's called locking ourselves into a destructive future. So that's great. Yeah. There are lots of alternate cooling technologies, alternate building design systems, passive design. We have such a rich tradition of all of this. We're not without tools here. We're not waiting for a new invention. We don't need any more R&D. We already know what we need to do. We just need to learn how to apply it in our context. That's another sign of hope. Yeah? There are also ways of saying that instead of cooling buildings, we need to cool the people, basically. Right? The entire air volume doesn't need to be cool. I just need to feel cool. So there are different ways of thinking now. You must have seen this, by the way, when you go to some of the more modern sort of public spaces like airports, for example, you know, the air handling unit or the blower is much lower than the ceiling height. You know this now, right? You see them right above, for example, the check-in counter or something, or even here. Okay, it's not the full height. The throw of air is from there. But imagine if it was even lower. Why do I need to cool that air? I don't need to cool that air. I need to cool us. So we can change those ways of cooling, even if you use air conditioning. Yeah. And there are lots of softwares available to help you decide whether this solution is better. And beyond softwares, also there are many other things. Okay. Some of the other interesting things. There is already a guideline that has been issued based on our inputs actually for integrating energy efficiency in undergraduate curriculum that was published a few years ago. How many of you know that this guideline even exists, teachers? Do you know that this guideline exists for integrating energy efficiency and sustainable cooling in undergraduate education curriculum in India? Published by the Bureau of Energy Efficiency and the Ministry of Environment and Forests. And we were part of actually influencing this. What we've done with BTU is another level, but this was a start. Yeah? Yes. Now, very often when we go to colleges, they say, oh yes, we have very committed teachers. Very good. We need passionate, committed teachers. But that is not enough. Because if that teacher moves to another school, then all the gains are lost for the institution. Also, we need all teachers to be doing it. Why only some teachers? So what we're saying is, yes, we do need passionate, devoted teachers, but what we need is systemic curriculum change. This needs to go into the very DNA of the curriculum. Everything needs to be rethought. How is this helping the future of civilization? How is this helping the future of the planet? Not just your client. Yeah? So that's what we're talking about, and that basically is what we've achieved with BTU actually. And tomorrow Savita is going to talk a little bit more about it. Okay. Now the fact that, you know, Anuradha here was saying that what we really need to also understand is that we are not talking about Mars and we are not talking about the future. We are talking about what is happening now. There are plenty of examples now, today, that prove that all of this that I'm talking about, all the solutions, have already been invented. We are just not applying them enough. So, right now it's proven that the energy consumption of conventional buildings is 50% more than the energy consumption of efficient buildings. That there are many other benefits of, for example, during COVID we realized, right? A lot of you must have known that there was suddenly a lot of interest in naturally ventilated buildings. Yeah? And naturally ventilated buildings make you feel healthier, fresher. How many of you prefer sleeping in fresh air than in a box, an air-conditioned box? If you had a nice terrace, like a small cot on the terrace in a school and you had some way of controlling mosquitoes, you would of course sleep in fresh open air, right? Same thing with your workspace. Would you like an architecture studio that was an ice box, or would you prefer a beautiful, shaded, naturally ventilated studio space? Which form would you go work in? And it's the same for everything. Don't ITP employees prefer that? They do actually. I don't know why we keep giving them those glass boxes with tinted windows and making it look like horrible imitations of architecture of Las Vegas and Dallas and all of this stuff. Everybody prefers this, and it's been proven that you have lesser sickness in those buildings. So you as an architect would say, I'm designing a building that's going to lead to what's called, you know, the sick building syndrome. How many of you have heard of this term? Anybody designing a commercial building, please tell me you've heard of this thing called the sick building syndrome. No? You've heard of it, right? Most people think it's the boss that's horrible. Of course, very often bosses are horrible. I can tell you I am one. But it is not just the boss that is horrible. It's actually the building that is horrible as well. big thing that we keep hearing. Teachers after the session will be like, "Sir, can you do any R&D project with us?" So I often ask this question. When was soap invented? We've done this training kind of sessions in about 50 colleges in India now. In almost no college bathroom do you see soap. During COVID it appeared magically for some time. And now that COVID is gone, soap is also gone. So my question is this. If we've invented soap such a long time ago, we've done so much R&D, but we don't apply that, then what is the point of doing more R&D? So what we've said is now we need another thing, is we need what's called R&D and D. Research, development, but more than that, deployment. We need to apply, we need to stop getting interested only in the new, and at the moment the new thing is done, move on to the next thing, and then move on to the next thing, and then move on to the next thing. It's like this iPhone life, you know? Oh, and now I have version 7, it's already old, it's slow. Oh my god, look at iPhone 7, how slow. And then we want iPhone 8 and iPhone 2049 or whatever. It's never ending. This obsession with the new. But we forget to apply Golgoppa's principles in our buildings. Of that incredible air tunnel effect. You've been there, you sit there, there's no air out, no breeze outside, it's still, and you sit there and there's this breeze blowing in through that window. Which building here achieves it? So, we need to be really preoccupied with research development, but don't forget the final D, deployment. Okay, now solutions exist. How many of you have designed green buildings in your projects? Or if I were to ask you right now, all of you close your eyes, let's do an activity. Please close your eyes. I'm not going to take your phones or anything away. Don't worry. Maybe if I do, it's a blessing to you actually. So please, everybody please close your eyes for a second, okay? And imagine a green building. Imagine an actual green building that you could design. Yeah? Okay, when you have a few pictures in your mind, you can open up and share, please, what was the most prominent feature in this green building? What made it green? What feature did you see? Come, let's Riddhi, Vishwanath. I know your names because they came to pick me up. You'll have one picture that came to your mind.
Larger openings.
Larger openings. Okay. Better ventilation. Really, you saw this? Or you're just saying this because I know that you know that that's what I want to hear? You really saw this? That's great. Wow. Okay, what else? How many of you imagine solar panels? Come on. Right? All of us imagine solar panels. We often go straight to renewable energy. It's not a problem, it's good. Renewable energy is good. But what is the point of renewable energy in a building that is leaking cool air, has got glass facade, has oversized spaces, has open plan kitchens where the kitchen heat is battling the AC, like creating this nice Mahabharata? And then we want to put all of that on renewable energy? It's madness. It's like trying to press the brake and the accelerator at the same time. Can you ever stop a car like that? We want to press the brake, right? But at the same time, I want to accelerate the whole thing. So consume a lot of energy, but just put it all on renewable energy. So there is a great framework called Be Lean, Be Mean, and then Be Green. Not the other way around, please. Please not first go for green energy. It is important, but first what you must do is you need to reduce the amount of energy consumption to begin with. You need to do a better envelope for your building. You need adaptive thermal comfort, which is try to have mixed mode buildings. and recognize that the whole world does not need 18 degrees cooling. This is a white, Caucasian, male fantasy. It's a patriarchal system that came up with 18 degrees as the norm for cooling. But world over now it's been challenged. It's been proven that in naturally ventilated buildings, 28 degrees is enough if we have movement of air. All of that allows you to be lean. Then you can be mean, which means use better controls, So if there's nobody here, the thing shuts off and so on. Or depending on what the temperature is like outside, it modulates the openings to allow for filtered fresh air to come in mixed mode, etc. Better controls, better star rating system, and then after you've done all of this, then you can use renewable energy, but you have to earn your solar panels. It's not a privilege. It's not an entitlement, it's a privilege. So earn your solar panel. Okay, now this is actually true. This is an example of a real average office building in India and a best-in-class office building in India. Look at this energy consumption. Yeah? This average is 240 kilowatt hours, which is energy per meter square per year, and best-in-class is 1/4. Now, you must often be wondering, how do I convince my client that this building is the cheaper building? I know from my experience with working with lots of architects around me, including my sister, that most architects are incapable, and you can correct me if I'm wrong, you are not taught how to do life cycle costing of a building. I think, Professor, you must be teaching in building economics, life cycle energy consumption. Not just now, not just the construction cost. How many of you feel comfortable to do life cycle costing? They're telling me in 30 years how much your building will cost for 30 years of operation. How many of you know how to do this? So, okay, Professor Taksar is not looking backwards. Fine. Right? It's challenging. But do you agree that the sustainable building is actually cheaper in the long run? Do you agree? But we cannot right now, we don't have the skills to prove it. We in fact are defensive, saying, I'll say double glazing, I'll say better shading, I'll say reflective paints, I'll say cavity walls, I'll say buff foam, and they're going to be, what an expensive building this person is building. I'm never working with this person. Right? You'll go in defensively. What you should be going in with the confidence that I've built you the cheapest building that you could have got. Because on a life cycle basis, these buildings are all cheaper to run. Yeah? Okay, so we have to learn how to do that. Now this is perhaps the best example of a real life experiment in sustainable building design and cooling in the world perhaps. This is the Infosys headquarters in Hyderabad. Okay? How many of you have seen this picture before? You have, Professor. You all have. Great. Great. That's a great thing, but it's also a very sad thing. Because years later, after doing this for about 6-7 years, we still keep pointing to that one building. That means it's very unusual. Imagine if you had a world where one doctor knew how to save lives, and that doctor became famous. That would be an indictment of every other doctor. Or you had this one non-corrupt police officer that became famous. What does that mean? That means the rest are corrupt. So the fact that you keep repeating this case study of Pokhara building of Infosys is at the same time makes me feel good, but I feel sad as well. This should be so boring and ordinary from here on that we stop showing this building. Now what is this building? This building is the same design on both sides, exactly identical. Yeah? Same orientation, same building materials, same amount of occupancy, all of this. This one side has what's called radiant cooling. And we will talk a little bit about it if you want. But you know what radiant cooling is. It's got cooling panels rather than air conditioning. In the floor, in the walls, everywhere. That, and it has also, each of the cubicles there has a small fan. Because they keep that system at about 28 degrees, with a little bit of fan, that combination, for example, drops the energy consumption a lot. And this one side of the building is about 1/3 of the energy consumption of the other side of the building. It's proven. And they have 10 years worth of data to prove this. That the same building with a better way of designing just the cooling system can have this much of an effect. Yeah? Okay, so the story is this. We can, through our work, reduce kilowatt hours of energy consumption, we can reduce the greenhouse gas emissions, but more importantly, we can reduce the cost of these buildings. So it's actually a very economically friendly story. We are not building expensive buildings, people. We are building cheaper buildings. But just our horizon has to be a little long term. So more short term thinking is not going to help us get out of short term thinking. Short term thinking is what got us here. Short term profits, short term gains. Yeah, so we need to expand the horizon of the building. The buildings will stand for 30, 40 years. So learn how to do the life cycle costing of 30, 40 years and prove that it's much, much cheaper than another building that this person is building, which has got no insulation, no thermal mass, no concern for orientation, no ventilation. It's cheaper right now, but you're going to be paying through your nose to run this building. Okay, so I wanted to do a quick exercise, which I will do in a bit. Okay, so now, first actual exercise of the day. We all said that trees are an important part of climate change, of combating climate change. Yeah. Now we're going to do an exercise right now. So please bring out all your pens, papers, and your calculators. The first exercise we're going to do today is this. How many trees need to be planted, yeah, to account for the air conditioning that has been installed in this campus? Okay? So we're going to do a quick calculation to look at the carbon footprint of these ACs, and we're going to see how many trees you would need to plant to be a carbon neutral campus or a green campus. Yeah? Okay, so first is so the first, how many ACs do you think are installed in your campus? This is where I need some information from you. How many ACs, and do we have like a blackboard behind or something where we can write? Oh, I have a whiteboard. Okay. Can I bring this to the center? So, how many ACs do you think are installed? I hope some ACs are installed here. How many ACs are installed in this campus, approximately? Across the library, labs, professors, anybody? 30 ACs. So more, okay. We have a bidder. Who's bidding higher. Another is saying higher than 30. 50? Anybody wants to go higher than 50? Let's go to 101. 50, chalo, 50 is a good number. Okay. He's getting it. Okay, great. Okay, so 50 ACs. Yeah? Okay, we also need to know what the approximate size of those ACs is. Are these 1-ton ACs, 2-ton ACs? 1.5? Okay. Plus there are these kind of central ACs. How many of these central ACs are there? Can we turn the lights on there? Okay, so one is you have some sambar I can dip it into or like black dal actually. Yeah, dal makhani that tastes good. Okay, so there's 50 regular ACs, 1.5-ton Okay? 50 into 1.5 is how much? 75. So there's 75 tons of regular AC, plus how much of the central kind of AC must be there? There's only one? Okay. Library? Two. Library must also be there. Centralized AC is one. Okay. How much is the coverage of that? 10, 12? Okay. So to be, just let's take it as 100 tons totally on this campus. Yeah? Let's allow for some growth as well. Yeah? So 100 tons of AC are there on this campus. Okay. Now, we also need to know approximately how many hours do you think that AC runs per day on average? How many hours? Okay, so first is, okay, can you see here? Okay, so what is PR? PR is tons of refrigeration is equal to 100 PR. Okay? But do you know what this TR means? Why is it called tons of refrigeration? How many of you have wondered what is this ton of refrigeration? Is it the weight of the actual AC? 1,000 grams is what? No. What is 1 ton of refrigeration? Why do you call it a 1 ton AC? Volume of the room. Okay, does somebody really know? We're just guessing here. Okay, and this answer is going to surprise you. Okay, if you had 1 ton of ice and it melted over 1 day, the cooling you would feel next to it. Really, this has come from that. The amount of cooling that is provided by 1 ton of ice melting to the air around. Right? You agree that when ice melts, it cools whatever's around it, right? So if you were to put 1 ton of ice and allow it to melt slowly for 1 day, that's how much 1 TR of AC makes you feel cool. That really is actually the basis of TR, tons of refrigeration. 1 ton of ice cooling over 1 day. Yeah? Okay, so, and just a side fun fact. Okay, so you have 100 TR. Okay? Now, hours of operation. 4? Really? 4 hours per day? 6 hours? Okay, we get 6 hours per day. 6 hours per day. Okay? Now, we have 6 hours per day. We also need to know how many days a year. How many days a year do you think it runs for? 240? 250? 250 plus 82. Okay. So, days of operation per year is equal to 250. Yeah? Handwriting is not very good. Never been good at handwriting. Okay. Yeah, 250. Okay, you got the basic parameters here. Yeah? The only thing we will need to know now is approximately what's the star rating of this AC. What are the typical star ratings? You know the star ratings, right? What is the star rating around? 4? Okay, let's take 4. 3 or 2? Okay, let's take 3 then. 3 is actually the most average star rating in India right now in the market is around 3. Okay, so we take a 3-star AC. Okay, star rating. This is important because it tells us star rating. 3 star. Yeah? Okay, here we are ready to go. So, 1 TR is how many kilowatts of fluid. So, there are some conversion factors here. Okay? So, 1 1 TR 3-star split AC. Okay, so these are primary factors, I'm telling you. So a 1 TR AC of 3 stars takes 1000 watts of power consumption, 1 kilowatt. You're going to get all this, by the way. So focus much more on the doing. This is all yours. Yeah. Okay. So how many kilowatts of energy? Not energy. Sorry. By the way, we have to make sure we keep kilowatts and kilowatt hours separate. Okay. Kilowatts is a unit of power or energy. Power. Yeah. It's a rate of consumption of energy. Kilowatt hours is energy. Yeah. So the first thing is we need to know how many kilowatts of power these ACs consume, and then we'll multiply it by the hours. That's how you get kilowatt hours, right? Pretty simple. Okay, so 100 TR will consume how many kilowatts? 100 into 1000, right? Because they are 3-star ACs, fortunately. Okay, so 100 into 1000 kilowatts. Yeah? Cool? Now, I want to figure out, so how much is that? 1 lakh, right? 1 followed by 5 zeros. Right? Kilowatts of power. That's crazy. 1000 watts. Sorry. That sounded like a lot. I was like, man, somebody's trying to hold down. So basically it's 1000 kilowatts. Not 100 kilowatts. Not even 1000. Sorry. Okay, so 100 kilowatts, not that bad. Something looks. 100 kilowatts of power are being used by these ACs. Yeah? Okay. Now, how many hours of operation do we have per day? 6. Into how many days per year? 250 into 6 is 1500 hours per year. Right? So, the next part is going to be we have, the second thing is we have 100 kilowatts into 1500 hours per year. So how many kilowatt hours is that? Given this is going out of 1 lakh. Okay, we have 1,50,000 kilowatt hours per year, right? 1,50,000 kilowatt hours. You get that, right? Kilowatts into hours divided by year. Yeah? Any questions? Anybody not following along, please ask. Okay, now. Okay. Yes. Okay, now what we're going to do. We are now going to figure out how much carbon emissions 1 kilowatt hour of electricity produces in India. Does anybody know, to make 1 kilowatt hour of power in India, how much carbon dioxide has to be generated by burning coal? Okay. So a good number to keep in mind is including all the losses in electricity. You know that in India there are about 30% of the electricity is lost between the generation and the consumption. Yeah? Okay, so currently in India, the emission factor, it's called the emission factor for electricity is about 0.89 kilograms of CO2 have to be generated per kilowatt of power consumed. But approximately 25% more energy has to be generated. So I have to generate generate 1.2 kilowatt hours, 1.25 kilowatt hours for 1 kilowatt hour to be available to me. So that factor has to be multiplied by 25% to get the real amount of carbon dioxide that gets generated for 1 kilowatt hour. Okay, so let's do this math. Let's take, okay, so if I start with 1 kilowatt hour, you can do cross multiplication, right? I end up with 0.75. Say 25% is lost, right? Kilowatt hours. Yeah? Correct? So, to get 1 kilowatt hour, how many do I have to generate? To get 1 kilowatt hour, how many do I have to generate? 1 divided by 0.75, right? Which is how much? 1.25? Is it 1.25? 1.3. Okay. 1.3 has to be generated, okay? So, I have to generate 1.33 kilowatt hours, yeah, to get 1 kilowatt hour here. And now, how much is the carbon footprint for generation? I said 0.89. Yeah? So, I have to multiply this by 0.89 kg. Okay, now the units of carbon footprint are always this. Keep this in mind. Kg CO2, right? Kg of carbon dioxide. But there is an E always you will see below it. Kg CO2 E. Now let me show you where this was, for example. Yeah. You will always, in properly written documents about carbon footprint, you will always see the letter E. Yes. See E? What is E? Why equivalent? Because of the fact that carbon footprint comes from multiple gases. So when you burn methane, burn coal by the way, you also release methane. So what you do is you multiply the global warming potential of methane with that number of amount of methane to get the equivalent carbon dioxide. Everything is converted to carbon dioxide, like the dollar. Yeah? So, the carbon footprint of electricity in India, bring it back to the slide. Yeah. The carbon footprint of electricity in India right now, according to the Central Electrical Authority, the CEA, publishes annual numbers for this. Yeah? So, it's 0.89 kg CO2 E per kilowatt hour. Okay? So, kilowatt hour cancels. What is 1.33 into 0.89? 1.18. Okay. So, now I wish I could lift this, but anyway, you have to trust me. 1.18 kg CO2 E has to be generated per kilowatt hour that I use. So now I've told you how many kilowatt hours we are using per year. 1,50,000. So now multiply that by 1.18 and you will get to know how many kilograms of CO2e are being generated because of your air conditioning. Okay, so we have some more markers here. Let's see. So the big answer is what? 1,50,000 to 1.18, right? Which we just erase calculation specifically. This one? This one. This one is like that black smoke that all this is. Okay, so CO2e. Now you can move beyond the term carbon footprint. For you, carbon footprint has become CO2e now, right? Is equal to how much is it? 67,000 kgs of CO2e per year. many tons of CO2 is that? 177, right? Is equal to, usually you will see most carbon footprint reported to in terms of tons of CO2 heat. This is different from the tons of cooling. Yeah? This is the footprint of your air conditioning on this campus. I have not even looked at the refrigerants yet. Okay? The refrigerant that this AC would need. We will even look at this in a bit. Okay, but first let's start with this. How many of you can visualize 1 kilogram of CO2? How much volume does 1 kilogram of a colorless, odorless gas occupy? Can anybody imagine a gas's volume? Unless you're a little bit high. You can't. Right? You can't figure this out. So, very often, to get a sense of whether this is big or small or how much this means really to make sense of it, we use the carbon dioxide absorption capacity of a tree as a way of knowing how many trees I would need to plant. That's a good sort of factor or a good sort of substitute. Right? Okay. So now one very important rule of thumb here. This is a good, useful rule of thumb for all of life. Is this number here. 1 ton of CO2 requires 4 trees to be planted in its whole life. Sorry? Over the entire life of the tree, which means one tree in its entire life absorbs only 250 kilograms in its whole life. Exactly. So, imagine if you were to plant 4 trees per ton of footprint. How many trees do you need to plant every year? 708. 708 trees per year just for your air conditioning have to be planted. How many trees do you think you have on campus right now? 5. How many? 5? That's fine. But you see the thing now? You see how difficult it is to do this with trees? And this is per year, like Professor Nansali was saying. How old do you think these ACs are? 10 years? 15, 20 years? You would have had to have planted 15,000 trees by now to just absorb the CO2 that is being generated from these ACs. Okay, we're going to do another thing. We're now also going to look at the leakage of the refrigerant and we will see how this is not insignificant. Okay, now, in the life cycle of an AC, you actually end up using, say on a yearly basis, your leakage is about, say 10-15%. Yeah? Then over its lifetime, you will, basically if you have a 10-15 year lifetime, you will actually be emitting about 2 to 3 times that initial mass. Yeah? Because every year you're leaking 15%, say it's a 15-year lifespan. Yeah? So 1 kg, 1 ton of AC typically has 1 kg of refrigerant to begin with. Okay? When you buy it, it has 1 kg of refrigerant. R22. Let's take R22. Yeah? So over its lifetime, let's say 3 times. 1 ton of AC will need 3 kgs of refrigerant to run. Yeah? Agreed? Okay. So remember this. How many tons of AC did we have? 100 tons, right? We had 100 tons of AC. Right? We had 100 tons of AC. Right? 75 was the split ACs and all of this, and we said 25 tons for all the central stuff. So how many kgs of refrigerant are there in this that they're going to use in its whole lifetime? 3 kgs of R22 per lifetime, right? Per ton per lifetime. R22 now? 300. Your ACs will use 300 kgs of R22. Is equal to 300 kgs of R22 over how many years? What's the lifetime? Let's say 15 years. Okay, over 20 years. Okay, so over 20 years we will actually have more kgs. But let's for 15 we came up with 3, so let's say 15 years. Okay. We are trying to find out the additional footprint beyond this per year. So we have to divide it by 15 years because this leakage will happen over 15 years, right? So I need to give only a portion of it to every year. I can't give it to the 1 year. Make sense? Okay, so 300 kgs of R22 for 15 years. So how many per year? 20. 20 kgs of R22 are leaking out per year. Can I just add the tonnage? Can I just say that the answer is 177.2 tons of CO2? It was 170 tons of CO2 plus 20 kgs of R22 per year. So is the answer 177.2? This is 0.2 tons, right? Into? Yes. I have to convert this 20 kgs into equivalent of CO2. Right? Because each of these kilograms of R22 is equivalent to 1,800 kilograms of CO2. So I have to multiply 20 with 1810. 20 kgs of R22 into 810 kgs of CO2e per kg of R22. Kg of R22 cancels. What is 1810 to 20? 36,200? 200. 36,200 kgs of CO2e, which is 36.2 tons. Right? So that has to be added to 177. How much is that? 177 plus 36.2. 213. So the real footprint of your ACs, including the refrigerants, is 177 plus 36.2. That is 217. So the number of trees that will be planted is how much? 8. Okay, so it's 177 plus 36.2, which is 213, right? 213.2 tons of CO2e per year, which is equivalent to how many trees? 852 trees per year. Have to be planted. Okay, so you've done something pretty complex here. Yeah? Okay. Now some simple rules of thumb to also keep in mind that if this much tons of air conditioning, 100 tons of air conditioning, how many fans could you have been running? Here you go. 1 TR of AC avoided is 25 ceiling fans. So at 100 TR you could have been running 2,500 ceiling fans could have been running. Yeah? Okay, so these are just some rules of thumb for you to keep in mind. It's useful for further calculations as well. Oh, my battery is running low. Okay, so we did all of this actually. Yeah. Okay, one other thing before we move on to the next section is ask us, instead of doing all this work on changing curriculum, why don't you all just work on improving efficiency of ACs and all of that? So we came up with a way of figuring out how many tons of CO2 our program causes by getting all of you all to perhaps design buildings with lesser energy consumption. So we came up with what's called the negawatt potential. How many of you heard of the word megawatt? Megawatt means megawatt, generating of the watt. So there's a new term called negawatt, which is negative watt, avoided watts. And do you agree that negawatt is actually better than megawatt? Because for megawatt you have to generate coal. For negawatt you have to generate ideas. So that is about coal mining. Here you are mining your mind. You are generating ideas from your mind to generate megawatts. So what is the negawatt potential of your college? Say you have an intake of 40 students per year. Happens to be this case here. So we did a calculation actually to prove that there is no better way to spend money by the Ministry of Power and Environment in India than to pay for curriculum change. How do we prove it? We said there are 40 students per year. Say 30% of them graduate into practice. Maybe not everybody goes into architecture. They take about 4 years to start leading design. They say complete 1 billion project a year. The projects that your college will be generating, sorry, I need to put power into the. Yeah, I have it. I don't want to take running out of power as we talk about power saving. For a bit. Okay, so what we did was, we said that your college, by the year 2050, with all the students already practicing, will have generated about 3,445 sustainable cooling projects. Yeah? Okay. And we believe that it's very easy to bring down the energy consumption of a building by 50% by applying good principles of passive design and sustainable cooling. Yeah? So the amount of power you will be saving by the year 2050 is equivalent to almost 208 megawatts. Now a typical power plant in India, a large thermal power plant, is 250 megawatts. So in a way your college could be avoiding literally the construction of one full thermal power plant by the year 2050, almost. And now here's the incredible thing about this kind of approach to change curriculum to reduce energy consumption is this. Currently in India it costs 5.3 crores to generate 1 megawatt of power. And we came up with the cost of our project. The cost of our project is 4,600 rupees per megawatt, which means a megawatt is costing 4,600 rupees. But a megawatt is costing 5.3 crores. But why does the government, for example, still have much more interest in generating the energy than avoiding it? It really begs the question, right? If energy efficiency is so cheap, Why does the Bureau of Energy Efficiency have a fraction of the budget of the Ministry of Power? Sorry? They want active energy, but saving energy is the same thing as active energy. Right? The thing is, this is not a big business. Here, the energy generation and the benefits are being spread to many more people. Imagine this will actually mean one power plant does not need to be built. So there is pushback from industry. Industry wants us to have more power. Because there are oil companies involved. There are coal companies involved. So we need to take back power literally, saying that we can generate our own power by energy efficiency. And the rest we can do through solar, etc. Yeah, so this is how we can really get out of fossil fuel consumption. Is a lot of energy efficiency, and then we do renewable energy. Completely fine. Yeah? Okay. So this was hopefully a nice exercise that got you a bit of a glimpse of what carbon footprinting is. Now what we're going to do is, I'm going to actually talk a little bit about what I think, because we've already done a lot of numbers. What, according to me, is one of the most useful cooling systems that can be applied into buildings, which is also of interest to civil engineers. And it's called structure cooling. Okay, so now we're going to look at what structure cooling really is. And then we will get into a couple more examples in the next session. Oh, it's 12:42 already. Okay. So maybe we take about 10-15 minutes and then 1 o'clock we break. Yeah? 1 o'clock. Okay. Okay, so to begin with, I have 3 questions. Okay, so air conditioning, do you agree that air conditioning is about cooling the air and throwing it on people? That's all air conditioning is, right? That's how we feel cool. So now my question is this. How many of you know about rat trap bonds? A lot of you know rat trap bonds? Rat trap bonds, cavity walls? Cavity walls, right? How many of you know of insulation like wood wool or cotton bag? Right? What is the principle that keeps buildings cool because of these things? Rat trap bond, wool, wood wool. Air. So air is actually a way to stop heat transfer. Right? Air is an insulating medium. So my question is, if it's a medium that is not designed for movement of heat, why are we using it to cool us? Because cooling means it has to absorb our heat. So that's a question to think about. Why do we have an industry based on using a medium that is not designed for taking heat from us? That's one. Second question. I give you 2 tanks of water. Yeah? And I give you a tap for 1 tank and an electric pump for 1. And you want to empty the tank. Which one is the most economical and environment friendly way of emptying the tank? A tap or a pump? Right? But now think about this. Your building structure is nothing but a tank of heat. For the sun, basically is just baking your structure. It becomes a tank of heat. But what do? Do we drain the heat from the walls? We allow that heat to come in, warm your air up, and then you pump it. Why are we doing this? Why do we not drain the heat when we could be doing it? And why do we pump the heat instead? I have another question to ask you. Yeah, okay. We'll get to that later. Okay, now I give you a final question. Say there was a heat transfer process that was linearly proportional to the difference of temperature, which means, what is your skin temperature right now approximately? Most of our skin temperature is what? 35, 37? Yeah? Okay. Now your AC is set at what temperature? 25? 25. So say about a 10-degree difference, yeah, between you and the AC. Now, imagine I gave you a system which was 4 times more efficient in terms of cooling you. What would the temperature of the AC have to be for it to cool me 4 times more? It's a linearly proportional system. I'm telling you this, that the amount of heat transfer between you and the AC is directly proportional to the temperature difference between you and the AC. So if I want 4 times the cooling, what would the temperature of the AC have to be? 30 degrees, even lesser than this, right? So it will be about -5 degrees. Yeah? Can you imagine what kind of energy would be needed to have an AC that was -5 degrees? How much cooling you have to put in? Okay, but now imagine that for 4 times the cooling, I need only 2.5 times the amount of difference. Which means, so radiant cooling, yeah, the principle of radiant cooling is proportional to 4th power of the temperature difference. So if the difference between 2 places is 2 degrees, so say the AC is only 2 degrees lesser, if I were to double that difference, I would get 8 times more cooling. Now radiant and structure cooling is proportional to the 4th power of the temperature difference. So if I gave you linear proportional difference versus 4th power, which one would you choose? 4th power, right? But we are using a system that is only directly proportional, which means to double the cooling, I have to double the temperature difference. Whereas with this, I just have to increase the temperature difference by about 2 degrees. Okay, so now we are going to look at a system that has all these benefits. It does not use air, it drains the heat rather than pumps it, and is proportional to the 4th power of the temperature difference. Okay, and that the way you do it is by using water. Now, water versus air, which one is a better medium to pull out heat from you? Water. Do you agree? Water is more effective at pulling out heat. Can you give me an example of why that is so, or why do you say it so convincingly that water is a much better way of cooling people than air? What example do you have in mind? Wet cloth, right? We keep it under the fan or on the window so that all the air that goes through makes it feel cool. But that's evaporation. But I'm just asking you, water's capacity to pull heat, or what's called its heat capacity. You've heard this in school. Water has high heat capacity. So one good way to prove it is, if say I burn your hand with a candle right now, and I give you 2 options. To put your hand under a fan or under a tap of water, what do you choose? Tap of water. So water is so effective at absorbing heat than air. It is 3,400 times better than air. Which means 1 liter of water would have the same capacity to pull heat from your body as 3,400 liters of air. Which is why ACs have to run at such a high speed to give you a little bit of cooling. Whereas a little bit of water spraying will make you feel equally cool. But of course, we're not talking about buildings where water is being sprayed on people. But what we're saying is, with that water, we can cool the walls. And that is what structure cooling is. So what is structure cooling? Structure cooling is a situation where occupants feel comfortable if the surrounding surfaces are below the body's temperature. So rather than me being victimized by cool air with a drafty kind of cool air, I can spontaneously lose my heat if that wall was cooler, it's magical. If this wall is cooler, I feel cool. Do you have an experience of this in your life? Have you ever experienced a situation where the moment you enter a space where the wall is cool, you feel cool? Where? Gol Gumbaz. Another example. In vernacular buildings. Right? Or if you go to the basement of most buildings, basements are cooler because the sun has never hit those walls. So it pulls heat out of your body rather than cold air being thrown onto you. So that is what structure cooling is. Okay, now the whole idea of structure cooling rests on what's called the mean radiant temperature. Basically what it means is, if I were to stand in a room like this, so this is a sort of non-standard shaped room, I'm standing like a trapeze maybe, I'm standing here, yeah? Which wall temperature will determine my cooling feeling? That wall or this wall? Say that wall is at 30 degrees, this wall is at 20 degrees. I will feel more towards 30 or will I feel more towards my temperature feeling will be more like 20 degrees? 20. So mean radiant temperature is a concept that is often ignored. Okay, I won't get into the details of it, but basically what we want to try and do is we want to keep the temperature of all the walls below my skin temperature, which is what, 35 degrees. All I have to do is, if I drop that temperature by 10 degrees, remember, unlike AC, in AC 10 degrees leads to a certain amount of cooling. But here 10 degrees leads to much more cooling because radiation is proportional to the fourth power of the temperature difference. So to get the same degree of cooling that I feel from an AC, I just need to drop it by 2 degrees actually, because it's 2 to the power of 4. That is 16 times the temperature difference, which otherwise I would have to keep the AC at 16 degrees lower than me. I would have to keep the AC at 20 degrees around to get the same cooling that I will get by keeping this at 2 degrees less than my skin temperature. Isn't that whack? That's crazy. Yeah? Okay, so, by the way, a very interesting chart. This has been put out. This is an interesting historical fact. This chart was published by what's called the American Society for Heating, Refrigeration and Air Conditioning Engineers many decades ago. Since then it has been pulled from the public domain. Because this chart basically says air conditioning is the least effective way to cool people. Okay, look at this chart. Okay, so this chart, let me just explain. This is the temperature in Fahrenheit. Yeah, human temperature is how many degrees Fahrenheit? 98. Right? That's a well-known number. 98 is the human temperature. Yeah. Now this chart is showing you the amount of heat loss that the body experiences through different mechanisms of radiation and convection and evaporation. Okay. Now what does it mean the human body experiences evaporation? What process in our body creates evaporation and cools us? Sweating. Right? And here is radiation and convection. So basically what this one is telling us is at around 98 degrees, which is the typical body temperature, the amount of heat that we are losing is because of perspiration primarily. Yeah? This is evaporation. Most of the heat loss is happening because of evaporation. But if you drop the temperature of the walls around, if you bring it, say, a couple of, about 20 degrees lower Fahrenheit, which is about 10 degrees in terms of degrees centigrade, then most of the heat loss happens by radiation. So the logic is to, rather than losing heat by perspiration, we'd rather lose the heat through radiation. And that is possible if you drop the temperature of the body, drop the temperature of the surrounding walls to a manageable temperature. That's the whole logic of it. Okay, so basically for you, building designers must keep the mean radiant temperature well below skin temperature. That should be the goal. And basically the idea is this. A person like this is surrounded by cool walls and the body radiates heat through the walls rather than you being cooled by the air. Okay. So I'm actually going to show you a real life example of this. So this is a test setup that was put up in Mumbai, in central Mumbai. I don't know because the colors is not very visible. But here is a concrete slab with pipes that have been laid inside the slab. So it's high density polyethylene. I'll show you pictures. Here is a tank. Actually, let me show you the diagram. Okay. So here is a slab with the pipes in it. Yeah. There is a pump in a tank, a two-chambered tank. On one side is the cooled water. On one side is a returned water which is warm, a little bit warm. And in between is what's called a heat pipe and a radiator. Okay, so what happens is, actually I have a video, but I don't know if we have Wi-Fi here. I wanted to show you a video. We have Wi-Fi and speakers here. Speakers also there? Okay. So I can show you an animation which will make it very easy to understand. You have a slab which is connected with pipes, and there is a twin-chambered tank, and water is flowing at a very nominal rate. So this is cooled water. Imagine the water is at about 20 degrees. So imagine you can use your underground water tank for this. Yeah. So you have about 20-degree water coming up and slowly making its way to the slab. The slab could be at about 40 degrees. Right? Baking in the sun, 45 degrees even, if you touch it. Now 20-degree water is coming in and making contact with a 45-degree slab. The average temperature drop would be approximately in between. So the water will come out at somewhere between 20 and 45 degrees, which is about 32, right? 32 degrees. Around 32 degrees, right? Yeah? So water will come out at 32 degrees and it will go through what's called a heat pipe. Now, a heat pipe is nothing but a bunch of copper tubes with a refrigerant which boils at normal temperature, but there's no electricity. So as it boils, it picks up the heat from that water. It rises and there's a fan, like a radiator fan, and I'll show you pictures. And that cools that refrigerant down and it keeps circulating without electricity, basically, just a radiator fan. That water comes back at 20 degrees and goes into the other side of the tank here. Basically, you have been able to cool the slab from 45 degrees, which would have been radiating heat to you. But instead now, you are radiating heat to it because it is 5 degrees lower than your body temperature. And just that difference creates a much greater reduction in air conditioning. You might still need to use AC, by the way. When it's very humid, you need to use an AC. But what you're doing is, a lot of the load of the AC has been greatly reduced because you're only using the AC for dehumidification, as it's called. But most of the body's cooling is happening through the radiation effect with structural cooling. Alright? Okay, so we try. Oh, you have to stop the so the way you actually do this is a real life example. Excuse me, in the back. Hi. So, this is a real life retrofit example. Yeah? This can actually be done in a building that has already been constructed. So the way this works is you lay 25 mm corrugated polypropylene pipe without any joints. So the key is very few joints over here. This is one long pipe. And then you cover it back with screen, with your plaster. So you can regenerate the flat surface. Then you have a small holding tank which is connected to an underground tank. This is the radiator and the heat pipe system. And this is the manifold. So each loop, by the way, is connected to a separate circuit. So that even if you want to take one down for maintenance, you can take it out independently. And the others are still operating. So you won't use basically everything in one connected loop. Yeah? Now this is example, and I'll show you many pictures of how the system operates and all that. This is an example of a real home. So this is in Mumbai. This is in Nasik. This is in Jaipur. So let's look at the worst example, as in the most stark example. In Jaipur, the average rooftop temperature was 52 degrees. The bottom was 45 degrees. With, this is DSC, direct structure cooling. This is without, rooftop with direct structure cooling, roof bottom with direct structure cooling. It went down from 45 to 28 degrees. Just this simple system. So imagine walking into a room where instead of it being 45 degrees, you are at 28 degrees. How do you, have you ever felt a feeling like this? Yes, you felt it in Gold Gumbaz, but one way to feel it in real life is turn on your AC for a short while, for about an hour or so. It will cool the tiles and the ceiling and the walls a little bit. You know, sometimes when we turn the AC on for a couple of hours, in the morning also when somebody comes in, they feel a little cool. That's sort of what this cooling feels like. And there's no draft of air. Yeah? And another fantastic feature of this, all these pipes can be used for running solar hot water. So if you're designing a building in Delhi, if you're designing a building which has composite climate, yeah, there you can run the solar hot water system in this thing, and you can get basically structural heating as well. So it's a very flexible kind of system. This is a very well-known auditorium in Mumbai called Veer Savarkar Smarak. It's near Dadar in Mumbai. This is about a 7,000 square foot roof over here, and this was retrofitted with structure cooling system over here. And this reduced the air conditioning needs by about 40% in this place. And Mumbai is very hard to not have air conditioning. So 40% reduction is a big reduction. As it is, we said, right, India's goal is about what, 33 to 35% reduction. This is good enough. So one opportunity would be as many rooftops that you can do direct structure cooling will reduce the air conditioning load. And it can also be used in curved surfaces. This is a museum in Gujarat where they have applied this system on a curved surface, including a flat surface. This is actually in a place called Sari in Gujarat. This is also to show you that it is effective even if you put it in intermediate floors. You must be wondering, but only the roof is exposed to the sun. Why do the intermediate floors need this kind of a system? But basically the truth is, once heat comes into your building, it's like water, it will trickle, it will find a way. So as many opportunities as you have to drain the heat out, we should be using. Yeah? This is an example of it being applied in a place called the Student Living Center in Gujarat. And there's another cooling system that they are also using. But you can see this is all being done retrofit actually. You don't have to do it only during construction. If you can, great. It reduces the cost because it's integrated in the slab. Now this is the beauty of what this looks like from the inside. From the inside you can't tell. So the great thing about this aesthetically also is you can reduce the size of ducts. Or maybe in some places you don't even have ducts. So this is like a ductless, no noise, no draft cooling system. And then a little bit of fan will be enough because you have dropped down the radiant temperature so much. Yeah? Now in terms of economics, remember we said that these are actually cheaper buildings. So the energy savings are about 33% because this is in humid places. In some places, you also need a little bit of AC to continue the dehumidification. So on an annual basis, you can say for humid places, not here, in Bijapur, you would have at least 50% savings. Yeah? But in a place like Mumbai, etc., 33% savings. But the great thing is that the cost per square meter for a conventional AC building is about 3,300 in Mumbai. This is actually 3,302. Why is it cheaper? Why is the construction cost also cheaper? So not only is it cheaper at the lifetime, but the first cost itself, the capital cost itself is low. Why? Even though there is all these pipes and this radiator and all this. Where are the savings coming from? Why is it? No, this is, yes, first time cost. Exactly. So you actually reducing the tonnage of AC that you're buying. So that savings in tonnage of AC and reduced air handling unit, everything is paying for these pipes. Basically. So if it's done at the design stage itself, it's actually a cheaper system to construct. Yeah, so that's structure cooling. And
But what would be the cost of one, say, 1,000 square foot house?
yes. So the cost per square foot right now is 1 second. I'll tell you. Yeah, this is about 3,000 rupees. It's about 3. This divided by 10, right? Per square meter. 300 rupees a square foot. 3 lakhs. Entire house gets it. Yeah. For an AC, right? It would be approximately how much is it per? They say about 100 square feet per ton. So you need 10 tons of cooling. And then the living room. Zero to 6. Right. They put a fan. Exactly. Right. 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 So you can reduce it. You don't have to do it for the whole house. You can just do it for one room. So where you're going to go for central AC, you should definitely do this. Because 10 tons of AC will actually cost you much more. Right. I guess it's possible. So, whoever is interested in actually applying this, there is a genius 92-year-old inventor. His name is Surendra Shah. He's the actual person who taught us about this system. He's 92 years old and he's still inventing, by the way. And you know which building turned him around? He used to be a very well-known engineer with Carrier India. For 25 years, he designed air conditioning systems. And he came to Gold Gumbaz. I will tell you the story. This is a very funny story. He came to Gold Gumbaz with his wife. After the whole tour where the person told him about the basement cooling and the thick walls and all this, his wife in Gujarati says, "Acha, to tame aa karo jo. This is what Carrier does in terms of cooling." And he said, "Absolutely not. This is not at all. We are nowhere in terms of the sophistication and the thought that has gone into cooling Gold Gumbaz. Carrier is actually trashing the planet." That moment changed his life. He turned around. He quit Carrier. He quit his career in air conditioning, unlearned all this humbug of air conditioning, and developed a way to make structure cooling possible in Indian buildings, conventional Indian buildings. He's 92 years old and he still is inventing new ideas. This guy. He's just unstoppable. This is all included in this. In the 330 rupees square foot, it is all included. By the way, in Mumbai right now, this cost has come down to about 180 to 200. This is old numbers. It's about 200 rupees a square foot to do this. It includes everything. The radiator. Yeah, there is a little bit of electricity for sure. But just for a fan, there's no compressor. Basically, there's no compressor in this. That's the key. Okay, so maybe we take a lunch break now for about an hour. Yeah. And then we come back and we start. So it's about 1:15, so at 2:15 we start? Yeah, is that good? Yeah. 2 o'clock? Okay. Yeah, no, I have to catch a train for sure at 5. Yeah. But I need to go and pack my stuff and bring it. I forgot, I didn't do it in the morning. So I'll just go and pack my stuff, be ready, and then I'll leave. Oh.